is now 12:02 p.m. Central Time, and I am your host, Dr. Matthew Richardson, and this is another stream of CosmoQuest Astro Office Hours. All right, so today's plan is to talk about all the fun with tides here on Earth. But before doing so, let me first go ahead and verify that I'm streaming. So if you've been to my previous streams, you know that this process might take a minute or more than a minute. But yeah, let's go ahead and open up Chrome and navigate over to Twitch to make sure things are okay so far. Okay. I see a little red circle for CosmoQuest, which typically indicates that there is a live stream, and I mean, right now I believe that I'm scheduled to stream, so yes, it is me. And oh, that's so cool. It's actually allowing me to pop out the chat like right here on the first go. So this is one of those days where Twitch and my OBS software, my computer in general, are just happy and they're working with me. I'm gonna go ahead and quickly say a hi all to everyone who's currently here in the chat. Hey Guido. Let's see. Say hi to everyone else. So as of right now, I'm seeing two people. That's Guido, which I've said hi to already. I'll say hi again. And Michael T. Mayer. Hi, Michael. All right. There might be more people here, but I mean, that's just how it works. Guido probably can see more people than I. All right. So let's go ahead and get into today's discussion on tides. So I don't think I need to like do any sort of definitions for tides. Of course, we all know tides. You know, the up and down motion of the waters here on Earth. But the major question is what causes those tides? So I'm going to actually put this question out to you guys, to the audience. What do you guys think causes the tides here on Earth? Let's make sure. It says 4 viewers at the moment. Okay. Yeah, let's see what my So yours says 4, mine only says still 2. So mine has not updated yet, which is unfortunate. All right, we got the moon. Hey, Michael T. Mayer. All right, we're international. Of course, we're international. The Weekly Space Hangout crew is international. So you see 7 people. Okay. This is all right. Well, that's cool. Well, hi to everyone else that I'm not seeing. If you say something in chat, I'll see your name and I'll make sure I say hi to you. But so far, I have the moon, and that's part of it. Yes, the moon probably is and I'm just going to kind of give it away. But the moon is the planet, is the body within our solar system that contributes the most to the tides here on Earth. And there's one more body that has also a contribution to tides here on Earth. So the moon was one of them. There's one more. And the other body being the sun. So what I'm going to do now, go ahead and Michael T. Mayer just said it, just as I said it. That's right, the sun. So I'm going to go ahead. I'm going to switch scenes and have this image here So it looks like the image originates from Britannica.com, or at the very least, you can see the image at Britannica.com. And basically, it's showing two different scenarios of an alignment between the sun, moon, and the earth, where we get different scenarios for how we get high and low tides here on Earth. One particular scenario with the far left portion of this image. Let me see if I can actually maximize this. I should be able to. Images may be subject to copyright, so I will say it again. This is not my image. In fact, in the lower left-hand portion of this diagram we're seeing here, it's copyrighted 2006 Encyclopedia Britannica Incorporated. So not my image. But basically on the left-hand side of this image, let me make sure that you guys are seeing exactly what I'm seeing perfect. And I see my face is blocking a little bit of it, but that's okay. And so basically what we're getting is that on the left side of the image, we have the sun, then the moon, then the earth, in that order. And so what's happening is we have basically high tides in the direction of this line that's being generated between the sun, moon, and earth. And we get low tides in the perpendicular direction. And for the right-hand side of the image, we're getting basically, in this situation, we have the sun, earth, and moon, but the line between the moon and the earth and the line between the sun and the earth are perpendicular to one another. And the high tide this time is actually along the line that's parallel to the moon and the earth line. So automatically what we get right here is that, and if you look at this, I mean, the high tide, yeah, the high tide is indicating that that's more of an elongation along that particular line of the water here on Earth. And basically what we see is that, the moon apparently, has the most dominating effect on the tides here on Earth. And so we're actually going to talk more so about, that's the qualitative effect, of course, of tides. We're going to talk more so about quantitatively what's going on with tides. We're going to want to make a comparison between the tidal effects of the moon on Earth's waters versus the tidal effects of the sun on Earth's water. So let me go ahead and switch my scene back. And also bring up my tech document. And so here is our problem we're trying to solve. Estimate the difference in tidal effects on Earth due to the sun and the moon. All right. I want to quickly check comments. Oh, I'm so sorry. Is my voice back to normal? I hope so. If not, I can try to play around with my sound settings to make sure it's corrected. Oh, that's beautiful. I'm talking about Michael's last statement. He's watching on a 78-inch screen TV. That's insane. Let me check my connection with Twitch. Or at the very least, let me check my OBS software. I'm getting a green light so far. It's not fluctuating or anything between yellow, green, and red. It's just all green so far. All right. Let's go ahead and get started with our problem. I'm not even too sure how long this problem will take. Because I kind of just thought it up in about the last hour prior to the stream. Hey Bill, how are things going? All right. Okay. So where to start? Well, we need to be able to generate some sort of equation for, I guess, tidal force. I'm doing fine, thanks. Huh. Now, again, guys, this is kind of one of those problems where we're working through it together. So, we need to generate tidal force. Tidal force is basically going to be a situation of where you have one body acting on another body in such a way that the gravitational force, let's say from body A, is such that it causes a differential force on body B. Okay. And we know it's gravity. So let's go ahead and start off with the gravitational force equation. So, no indent, gravitational force equation. This is something that has been pounded into my head over the many years in which I've been in school. So, this I know pretty well. I hope I know pretty well. Let's see, a line. We're going to end up getting that F underscore sub G, which is my little notation for gravitational force, is going to be equal to this ratio that I'm about to write out here. We're going to get G, let's say some big M, some lowercase m, over R squared. Oops, squared. Let's go ahead and typeset that. So this is our gravitational, well, this is the gravitational force equation as far as the magnitude is concerned. I'm not really concerned with vectors right now. So, let's do a little bit of tidying up here. All right. Oh, sorry guys, give me 1 second while I fix that. All right, there we go. So, we want to be able to calculate a differential force here using this equation. So we're going to do a derivative. We'll do a derivative here. And the derivative that we're going to do is df sub g with respect to distance, or r in this case. So just to quickly explain what this equation is stating is that the gravitational force between two bodies, one body with mass capital M, the other body with mass lowercase m, is equal to the gravitational constant g times the product of the two masses divided by the separation distance r between them squared. And so we're going to go ahead and calculate this differential force. And of course, the only reason why I'm calculating the differential force is because a tidal force is a differential force. So let's go ahead, no indent. So differential gravitational force. And again, I'm going to go ahead and copy and paste. And so the left-hand side of the equation will be modified such that we now get a fraction. We're going to get df sub g over dr. And now this side of the equation will be modified such that we're taking the differential with respect to r. So d over dr of this. And I'm just going to quickly put this in brackets. Hopefully that comes out right. It did not come out right. I've done something wrong. Oh, left. I put another right here. It should be left. All right. So this is the beginning of our differential gravitational force. And so given that we're doing this with respect to r, g and the two masses are going to be constant, of course. And so we should end up getting, I'm just going to go ahead and copy and paste to the next line. Let's quickly check. So m is equal to the mass of the column of water of some length. So yeah, we're just gonna say m is equal to the mass of the water on Earth. Yeah. And yes, yeah. I like the way you put that actually. Some column of water. Yeah, that's a better way of putting it. Um, so we have two gravitational forces acting in opposite directions. So ignoring the sun for the moment. So in that situation, if you're only considering just the Earth and the Moon, then all the water on Earth would have a gravitational attraction towards the Moon. If that makes sense. I'm not too sure about the if you're ignoring the sun, I'm not too sure where the other gravitational. Well, also then you also have the gravitational attraction of Earth on the water. So yeah, I get what you're saying. And of course, if there's going to be any sort of so given that we do have tides, that would have to imply then that the gravitational attraction of the Moon on water is greater than the gravitational attraction of Earth on the water. All right. But yeah, definitely good points to point out there, Michael. Let's see. So we're going ahead, we're doing this derivative. And so we're going to end up getting, and if I'm not mistaken, the derivative of that would just basically give us it's r squared. For some good reason I'm having difficulties doing a derivative right now. So gmm times, and let's just put the r squared up top. It's r to the negative 2 power. And so, oh, we get a factor of negative 2, I believe, up top. If I'm not mistaken. So we'll get a factor of negative 2. And the denominator will now become r cubed. If I'm wrong, guys, let me know. For some good reason, my mind just kind of blanked out there on how to do derivatives. I hate it when that happens. Every now and then it happens. I will quite literally sit and look at an equation and be like, how do I do this? All right. So, negative 2 gmm over r cubed sounds about right. All right, so far so good. Now note though, this is a differential gravitational force. For tidal force, we're going to want to think about macroscopic changes in force. So, I'm gonna take a quick moment and look at comments. Does it increase by? Does the factor increase by? Is that right? I thought that whenever you take a differential, that the exponent goes down. Oh man, Michael, you got me thinking here. Let me. You know what? We're gonna let the internet decide this. We're gonna let the internet decide this. So guys, this is what science is about. Even scientists at times forget things. Let's see. I'm gonna go ahead and switch scenes, and we're gonna go back to the internet, and we're gonna bring up a derivative calculator. So for any of you guys out there who happen to have situations like me, where you forget how to do things, the internet's your friend. It will solve things for you. All right. So I'm really only concerned about the R. So we're gonna set GM and the G and the two M's to equal 1. And we're gonna make our equation to simply just be 1 over R squared. Or 1 over X squared, excuse me, because this calculator requires that it's that. Alright. So d over dx, and let's make sure that you guys can see what I'm seeing. And let's kind of make this bigger. Perfect. So that is the derivative that we're concerned about. 1 over x squared or 1 over r squared. Let's go ahead and go. It's going to do some stuff. It's going to do some stuff. Okay, we're good. We're good. So according to this, it should give us, excluding our g and our two m's, we should get negative 2 over x cubed. So I think I'm good. I think I'm good. Let's see. Oh, thanks, Michael. Okay, thank you. Hey, I am Hop, or I Amy Hop, or I am IHOP. Hey, how are things going? Hey, Binary Ablaze. Does it go down or approach 0? I'm assuming you're talking about the exponent. Oh, I'm sorry to hear that, Guido. I really do hope that things go well from here on out with the stream for you. But Binary, is that a good idea? The internet is your friend. That's what I'm gonna say. Is the internet's your friend? And so as of right now, the internet seems to be on my side. So yeah, it goes down. In fact, a good way to remember it is if ever you're dealing with 1 over x, you cannot use the same derivative method that I'm using now because you get the natural log of x as the derivative. So yeah, it would have to. Yeah, it should definitely go down. Yeah. Thanks. I am IHOP. I like that name. And again, guys, around this time is lunchtime for me, so anything I could think about is like being related to food. This makes me get extra hungry. All right. So we're going to go ahead and switch back to scene and go back to our problem. And so our derivative's good. So df dr is equal to negative 2 times g times m divided by r cubed. So far, so good. However, like I was saying, this is a differential force, and we don't want a differential force. We want to be able, well, we could use a differential force, but we want to be able to take into consideration that tidal forces are more of a macroscopic thing. So we're going to use a little trick here. We're going to go ahead and use a proportionality trick and state the following. So no indent, proportionally, or let's put this, let's put tidal force, proportionality, let's put that. I think that should work for now. And let's go ahead and put a line, I always check to make sure that you guys can see everything that I'm typing, and I'm seeing it's kind of, there we go. It's a little bit better. Oh, no, you can't see everything I'm looking at. Let me make this quick correction, guys. All right. And I'm just going to make that a little bit bigger too. All right. And so what I'm going to now state is I'm going to state a fraction where now I'm going to use delta f, where the delta indicates some macroscopic or some really large change. Delta F underscore, and I'll represent this as tidal force. So capital T over delta R. This has to be equal to any sort of microscopic changes in force or differential changes in force. And so, to solve for our equation for our tidal force, all we have to do is multiply both sides times delta R. And we get the following. So this will be our equation we use for our tidal force. And I'm going to go ahead and substitute in what we end up finding out for our differential equation portion of it all. Or not differential equation, but for the differential expression on the right-hand side of the equation. So I can go ahead and copy and paste. And we end up getting, this is our final equation. Okay. I realize this looks like a really big mess, but it's good. It's good to go. So this is going to be our tidal force equation that we're going to end up using. And so, and I'll quickly check comments. I'm not going to lie, I am IHOP. That is actually quite impressive. I was not taking calculus in high school. I actually didn't get to learn calculus into college. And boy, oh boy, the first calculus course wasn't bad. I actually loved the first calculus course. It was actually quite easy. Calculus 2, still not so bad. You know, difficult, but not. It was challenging, but not bad. Calculus 3, oh my god, nightmares. Calculus 3 was nightmares. Yep, that's it, Michael. Oh man. So, given that you said that, Michael, in my Calculus 2 course, I'm going to use his first name, of course. I mean, you still would know the guy, but his name was Jake. I think he was 13 years old. In my Calculus 2 course. For a second, I thought that one of my other classmates kind of brought their kid along with them. Until I found out the truth, that there's this 13-year-old kid in our class doing calculus better than us. It tripped me out. I mean, yeah, but he was brilliant. I mean, baby genius, quite literally. He was impressive. But that's actually a cool thing to know, though, Michael. Was this formal training in calculus, or this is something you were doing in your spare time? And yes, Binary Blaze, IHOP. I'm thinking the same thing. Thinking the same thing right now. All right, I'm gonna go ahead and continue with the problem. So we can use this equation for our tidal force from the two different bodies acting on Earth's water. That is the sun and the moon. And so Wow. Man, Michael, that's impressive, man. So 13 and 215, well, with boys. So roughly the average age was like 15 years old of the class. Wow. You guys are doing calculus. But you know what? I wouldn't be shocked now if calculus became, the norm for like high school aged students. Given technological advances, I mean, I would kind of almost, expect for calculus to be in high schools now. It wasn't so. I don't think it was a really big thing when I was in high school. In order to take calculus, you had to take like an what do they call those courses? An AP course, like AP calculus. But now I think it should be like mandatory. Even to say that you didn't do too well in your exams, the fact that you were able to still comprehend it. I mean, when I was 13 years old, if you put a calculus, any sort of calculus in front of me, I wouldn't have, well, wouldn't have been the word I would have used in a sentence. Oh, okay. All right. Okay. I'm talking from the perspective of, yeah, of being a US citizen. Okay, that makes sense. That makes perfect sense actually. Cuz even when I was an undergrad, um many of the Asian students that I encountered were really good too. um all right. So, we can go ahead and use this equation for the remainder of our problem. And given that we're going to want to make a comparison between the tidal force of the sun on the earth versus the moon on the earth, we're going to go ahead and use division. We're going to divide the two. And dividing the two is basically the same way as saying taking the tidal force equation and dividing it into itself, where the numerator will have certain properties that are related to the sun or the moon, and the denominator will have properties related to, or the variables be related to properties that are associated with like the other body. That might be a little bit easier if I just write it out. So I'll put this as tidal force comparisons between the moon and the sun. Tidal force comparison between sun and moon. All right. So we can go ahead and type this out. And so, like I said, we can just divide the equation into itself. And basically, we get the following. I mean, you guys can, of course, always check my math, but I'm just going to write it out given that I'm able to just see what I'm working with here. Are you guys seeing things properly here? Yes, you guys can see everything. So let's scroll down a little bit. And let's put delta F sub t over delta F sub t. And I want another subscript. Let's put sun. And I hope this works. Let's put moon. Let's see if it can actually even do that for me. Okay, it doesn't like that. There's another way to do this. Because I want to be able to indicate that one's for the sun and one's for the moon. All right, there might be a better way to write this out, but for right now, I'm just going to stick with this. And equals, and given the equation that we're using above, I'll just go ahead and write that out too. So fraction this over this. And so now I need to make sure that the variables on the right-hand side of the equation are correct. Of course, the -2 will stay the same, the g will stay the same. The mass in the numerator, the capital M in the numerator, will have to be for the sun. So M underscore sun. The lowercase mass is going to be for water. We'll just put water, or W for water. And the distance, or the variable R, or in this case the R cube in the numerator, that R is going to be the distance between the water on the earth and the sun. We can kind of think of it as an average distance. So I'll put up here R underscore sun. The delta R in this case represents the change in length over which our differential force is being applied. So it represents that length over, as Michael was stating earlier, that column of water. It represents the height of that column of water. So delta R is going to be the same for both the numerator and the denominator. And so in our denominator, we're going to basically get -2g stays the same. The capital M now in this situation is the mass of the moon. And the lowercase m is going to be water. And the R is going to be the distance between the moon and the water on Earth, which for all essential purposes is the same as the distance between the moon and the Earth. In the same situation for the R underscore sun. All right. So far, so good, and it looks like I just made that so much more complicated by adding that information. But we're going to go ahead and reduce it now, though. We're going to simplify it. I'm going to quickly just check some comments to make sure I'm not missing anything. I am so sorry. So what? Okay. So Anbu0123, first off, welcome to today's stream. So what exactly is not making sense? Well, firstly, let me say this. The objective of today's discussion is to estimate the or basically compare the effects of the tidal force of the moon on Earth's water to that of the tidal effect of the sun on Earth's water. And so what we're doing is we're making a quick calculation for this. And to do the calculation, we're using the concept of tidal force. And so as of right now, I've calculated the ratio of the tidal force of the sun on Earth's water compared to the tidal force of the moon on Earth's water. If that doesn't make sense, then just let me know. And also, guys, everyone else is in the chat. Thank you, Guido, for commenting as well. If you're not clear what I'm saying, just let me know. And also, other people in the chat might be able to help out with the discussion. I'm going to go ahead and move along. And if it's still not clear, of course, I'm going to come back through it and talk about it. So basically, with the right-hand side of the equation, it reduces to the following. Yeah, you're right. I could. Typically, I would want to use like a circle with a dot in the center of it for the sun. But I just simply put the whole word. That way, it's clear to everyone what that particular variable stands for. But you're so right. And this is a new comment actually. Nuno Jam. Welcome to today's stream. All right. So let's go ahead and do the ratio. And by looking at this, we should end up getting the ratio of the mass of the sun to the mass of the moon. For any of you guys that I did not say hi to, hello everyone. And I hope I got to Nuno Jam, because you're definitely a new person here. So welcome to today's stream. But yeah, so we get the ratio of the mass of the sun to the mass of the moon, and we're also going to get a ratio between the distance to the sun cubed, which is here, to the distance of the moon cubed as well. But they'll be flipped. So if I'm not mistaken, the moon will be up top in the numerator and the sun will be in the denominator. And we should get this. Or more easily put, we can move the fact that they're both being cubed to the outside. So I'll do that. Left, right. This will be cubed. And we can get rid of these cubes inside our brackets. And so this is going to be our final equation we can use for being able to determine the or compare the tidal force of the sun to the tidal force of the moon. Thank you, Michael. Thank you so much for actually clarifying that. I didn't realize that I didn't say that earlier. That is so right. So yeah, the subscripts are basically just indicating the object, and as Michael has already stated, the variables, the bigger letters represent the variables for the equation. And as Michael put, M for mass and R for radius. And the capital F is for force. And that lowercase t was the subscript t was to represent that it's the tidal force. All right. So now that we have this, we can go ahead and we can figure out exactly what what the comparison should be. Now, off the top of my head, I do not know these values, so I will have to look them up. So what we're going to do is we're going to go ahead and go over to the internet again. I'll open up a new tab, and we're going to type in, and the key thing here is that you have to make sure you use the same units. So let's go ahead and type in the mass of sun. And so this mass is being given in units of kilograms. So it's 2 times 10 to the 30 kilograms. So let's go ahead and go back. And let's insert that information in. So I'm going to start up a new line, of course. I want to make sure I keep my general equation. The good thing about making general equations is that you can always change the subscripts to be some other body. Let's see, tech shop. Here we go. Like, for example, if you wanted to try to do this exact same problem with like Jupiter or something like that, even though I don't think it would it would apply. I guess it could apply. I mean, Jupiter has a gravitational attraction on Earth as well. Um, all right. And so we're going to go ahead and put the mass of the sun in. So 2 times 10 to the, let's put times, and I believe it said 10 to the 30. And this was unit of kilograms. So now I need the mass of the moon is next. So let's go ahead and figure what that is. Figure out what that is. Mass of moon. Hopefully it gives it to me in kilograms. Perfect. So I'm just rounding. I'm rounding. So I'm just going to use 7 times 10 to the 22 kilograms. And so the mass of the moon is 7 times 10 to the 22 kilograms. All right. So far, so good. Now we need to figure out what the radius, or not the radius, excuse me, the distance between the Earth and the moon and the distance between the Earth and the sun. And so, let's go ahead and check chat because you guys might have already gotten this information for me. All right. So the distance between the Earth and the moon. Okay, it's in miles. That's cool. We can do it in miles. Huh. I like kilometers better. Or meters or something like that. But it's cool. We can do it in miles. It's 238,900 miles. All right, I'm going to copy that. And I'm going to turn this into scientific notation. And I'm going to also round. So I'm just going to say 2.4 times 10 to the 5 miles. So our moon, let's put that there. Let's copy this. Make this easier on myself. That way I can have a reference. So 2.4 times 10 to the 5 miles. So kg now just becomes miles. All right, and lastly, the distance between the sun and Earth. Now to actually make this this equation actually more accurate, I would want to deduct the radius of the Earth from both of these distances I'm using. But because the radius of the Earth, for the most part, I'm thinking is negligible for the calculation, I'm just going to ignore it. So what our moon really should be, our submoon, it should be the distance between the Earth's center to the moon minus the radius of the Earth, because all the water that I'm talking about here is at the surface of the Earth. However, what I'm thinking is that the distance between the center of the moon to the center of Earth is just so much more greater than the Earth's radius, to the point where the Earth's radius is negligible. And I'm making the same argument with I could definitely make the same argument with the distance between the centers of the sun and the Earth. But if you want to be accurate, you'd want to incorporate that as well, or more accurate. All right. So I'm going to go back one more time to the internet. And we're going to put distance of sun from Earth. There we go. All right. So that's 9.3 times 10 to the 6 miles. All right. Let's quickly do this. All right. So fraction. I can go ahead and just copy this and I'll paste it here. 9.3 times 10 to the 6. And as expected, all of our units should end up canceling out. Kilograms with kilograms, miles with miles. And now comes probably the most difficult part of this all, and that's just using a calculator to figure out what these values come out to be. The arithmetic comes out to be. All right. So I have 2, and that should be E30 times 2.4 E5, that quantity cubed. And all of this is going to be divided by 7 E22. And that's going to be times a 9.3 E6. And that quantity is going to be cubed. Huh. I am definitely getting a result that I was not expecting. I might have messed up with the math somewhere, actually. So what I'm getting is that the ratio should be roughly about 491. I don't think the ratio is that much. So let me check these numbers really quickly. And make sure that I'm not actually missing anything. The 2 over 7 should be a fraction. Of course, that's going to give me a magnitude of like roughly 10 to the 8 with that first fraction. Or 10 to the 7. So what do I get from this? Actually, that makes sense. Something isn't right here, though. Because if this is the case, that would indicate that the tidal force of the sun is greater than that of the moon. And that should not be the case. So just give me a quick second, guys, while I look at this real quick. All right, so moon, sun. What do you guys think? So I am IHOP. So definitely agree with you, Michael, on that. So binary blaze, do SI. So yeah, we don't have to worry about the units because it's ratio, so the units will end up canceling out. All right, so I am IHOP. Aren't all tides caused specifically by the difference in gravity? Yes, they are caused by the difference in gravity. But I've calculated what the differential force should be. If I scroll up, I've calculated an equation for the differential force here. So somewhere I've done something that's not quite right. M sun over R sun cubed, that's present. The mass of the moon should be down there. The distance between the moon and Earth should be up top, cubed. That's right. .500 times the tidal force. This is interesting. As I go through the math, I mean, this should indicate that the differential force of the tidal force of the sun is going to be 500 times, well, roughly 500 times that of the tidal force of the moon. But that doesn't make sense. As if you do a quick check like on internet, you'll find that the tidal force of the moon is greater than that of the tidal force of the sun. I'm trying to think if I've left anything out here in the equation. The sun is much farther than this. Let's quickly look at that, actually. Is that the correction? Oh! I missed a factor of 10, didn't I? When I did the conversion, it should be 9.3 times 10 to the 7. Let's see if that makes a difference. But then that still doesn't give me exactly what I'm looking for, I think. But let's see. Excuse me while I quickly look at this. Let's go back to our tech document. Let's quickly make this correction. Is that what you were saying too? 93 million miles, right. So 9.3 times 10 to the 7. And that might make up the difference, actually. So let's go ahead and quickly make the correction. So who was that, actually? Let me make sure. I am IHOP. Good job for catching that. So 10 to the 7 here. Let's go ahead and typeset that. And so if I make the correction of 10 to the 7, haha! Okay, that gives me an answer that I think makes more sense. I see that I'm not nearly out of time here, but let me quickly write this out. So I'm going to put approximately. .5 and typeset that. So what we basically get here is that the differential force of the sun, or the tidal force of the sun on Earth's water compared to the tidal force of the moon on Earth's water is roughly half as much of that of the tidal force of the moon on Earth's water. Therefore, meaning that the tidal force of the moon is greater. So good catch. I am IHOP. As you guys can see, Mistakes can be made. I told you this was going to be the hardest part. Catching those arithmetic mistakes. But the key thing, of course, is that whenever I solve any problems, I always try to make sure that I do it generally first and then throw in numbers later, because if everything works out with your algebra, then catching the arithmetic mistakes hopefully will be easier. But guys, I'm seeing that it's now 1 o'clock now, and I've definitely had fun doing this problem with you guys today. Oh, you can't see the numerical result? Let's see. Okay, perfect. So 1,000 times different. So actually, I am IHOP is thinking is actually not thinking, but is basically getting to a very important concept here with the tidal force. The distance of two objects is going to be far more important. Well, I don't want to say far more important, but it's going to be very important here because of the fact that we have that whole situation of the tidal force goes as 1 over r cubed. So yeah, the fact that it's cubed makes a very big effect, which is the reason why the fact that the moon's so close to the Earth is the reason why its its tidal force on Earth's waters is so much greater. Well, not so much greater, but it's greater. All right, guys, it was great. Thank you, I am IHOP for stopping by, and everyone else. Thank you guys for being here with us today, or with me today. Um, I should be back on Friday, and again, I'm hoping that Friday will be kind of like a research thing, where I'm actually talking about the research I'm doing now. So we'll see. But I will see you guys later. Bye. One more thing for anyone here who's new, if you get the chance, check out the Weekly Space Hangout Crew's website. Um, hopefully, someone can put that into the chat for me. I always forget to do this, but also if you get the chance, check out CosmoQuest. We're located at CosmoQuest.org. And all right, I'm done talking now. You guys go and enjoy the rest of your day. Bye.